Okay, I'm going to talk about Poisson process today. And Poisson process is nothing, it's just a random process. Random process is really just list of random variables. And I can have a discrete list in the sense that I have like x1, x2, x3, and so on. And each of these number x1, x2 are all random variables. Or I can have a continuous list in the sense that I will have like xt and t is just a real numbers here. So for each of any t, any of these t, xt will be a random variable. And Poisson process is just a continuous time like random process, like in this second case here. And it's going to be used to describe things that's going to happen repeatedly in the future. One of the examples is to model the arrival of packets to a system, to a lateral node, for example. And what I can do is like to model a packet arrive with a 1, and when there's no arrive, with a 0. So therefore, realization of xt, a Poisson process can be like this. So we may have like low arrival here, and there's an arrival, therefore we represent there's a 1 here, and no arrival again, there's another 1 here, and so on and so forth. So one thing I need to emphasize is that like xt is a random process here. So therefore, at each time instance, even though I'm showing this, there's no arrival here, you can think of like it's just we have no arrival in our universe, for example. I mean, some other parallel universe, maybe I have arrival at the same time there, and maybe I have arrival in some other time. And this is just the kind of basic arriving process. And actually, Poisson process is the simplest random process to model a arrival process. Okay, now I would like to describe Poisson process in more detail. Basically, as I said, like Poisson process is really the simplest random process to describe arrival. Basically, it assumes that two things. One is the rate is constant. You have the process is kept stationary. The arriving rate is doesn't change. And at the same time, we assume the independence of arrivals for different period of times. So for example, if I have a period of time here, this tiny delta, this period of time here, and the number of arrivals here will be independent of like number of arrivals in another period of time here. And typically, or like I should say, I guess the easiest way to explain Poisson process or the easiest way to derive Poisson process just using this model here by partitioning the time axis into very tiny delta. And for each of these delta, since it's very tiny, we can assume that it can either have an arrival or no arrival. In other words, it is not likely to have more than one arrival. And then in that case, let's say the arriving rate is just lambda is equal to 1 packet per second. Then if we think of like what's the probability that it will be arrival in this tiny delta here, it should be just equal to p. The probability would be just equal to lambda delta, right? That's because like if we set this as lambda delta, let's say p is lambda delta, what's the expected number of packets arrive within this delta? Again, it will be lambda delta, right? Because I will have probability lambda delta that I will have 1 packet that arrive, with probability 1 minus lambda delta with no packet arrive. So therefore, like on average, I will have like lambda delta packet arrive within this period delta here. Now if I consider 1 second here, that will have like 1 over delta so many slots, right? So because on average there will lambda delta arrive in each of these slots here, so therefore the total amount of packets arrive within this 1 second will be just lambda here. So get back our original lambda here. So therefore it makes sense. Anyway, I think like this is a very nice picture to remember, because this is really the only thing you need to know about Poisson process, really, because all the statistics of Poisson process can easily be derived by this picture here with this tiny delta. And what we are going to do is basically just pick a very small delta. We just add a delta here, and then like take the delta, take the limit to have delta going to 0, and then we'll get all the statistics for the Poisson process. Okay, the first thing we try to do with this picture here is to derive the interarrival time. The interarrival time is basically just the time that, like, let's say if you have arrival here, what will be the time that next arrival is going to be. And of course, like, because the arriving process is random, therefore the interarrival time here will be also a random number. So the best thing we can do is just to find the distribution of this interarrival time here. And of course, this interarrival time is continuous. So therefore, what we want to find is the probability density function. This is a continuous random variable. The PDF of this interarrival time t. So what we're going to do is first we're going to write down what will be the probability that, let's say, t is lying in a particular slot, like t and t plus delta. So basically, like, we have arrival here, let's say this is time equal to 0, and we have another arrival at this time t here, and this slot is basically t and t plus delta, and where t is equal to n delta, basically, like, we have n minus 1 slots here. Before that we basically have no arrival. If we have arrival here, then the interarrival time will be less than this t here, right? So we need to have no arrival here, and we need to have an arrival here exactly at this nth slot here. And then the probability will be, as I said, like, we need to have no arrival for the first n minus 1 slot, and because all of this probability all of these events we can assume to be independent, and each of them is just 1 minus lambda delta. It will be just 1 minus lambda delta to the power n minus 1. And then, like, okay, as I said, this is just the probability of no arrival for the next n minus 1 slots. Let's discover ugly. And then and of course we need to have an arrival in the nth slot, so we need to multiply by lambda delta. And what's the PDF of t then? It's basically, it's just the limit of the probability from t to t plus delta and over delta, right? So this will be just equal to this here. I substitute this down here, and I like to multiply by 1 minus lambda delta. I mean, it doesn't change anything because delta is very small. 1 minus delta, lambda delta is essentially just 1. Actually, we take delta is equal to 0, so it is exactly 1. But then, like, we will have, like, lambda 1 minus lambda delta to the power n, and n is just equal to t over delta here. I can write down here. Note that we have this limit equation here, that limit of 1 plus x lambda x delta over 1 over delta is just equal to e to the x. So therefore, like, we see that this part here is actually just equal to e to the minus lambda. So, and I should have e to the minus lambda to the power t and lambda. And that's basically our PDF. Actually I found a typo here. This should be f tiny t here, should be equal to this. And actually for this equation here, sometimes like I don't exactly remember it, but I like to work. I kind of remember it, but I guess like it's not difficult to show, at least like convince yourself this is true, because let's say if I take the derivative of both hand side, if I take a derivative of this side, of course ex is just kept an x. If I take derivative of this one with respect to x, I will have like lambda coming upwards, so I have like 1 plus x delta, and this I have this should be 1 minus delta minus 1, and I have, okay, this minus 1 doesn't matter much actually. Yeah, let me write this 1 minus 1. I might have like delta coming up also, 1 over delta, and then this inside have delta here, so delta go cancel here. I have 1 plus x delta, 1 over delta minus 1, but this is just equal to 1 plus x delta to the power 1 over delta 1 plus x delta. And again, because delta is going to be 0, this thing is just equal to 1. So therefore we get back the original expression. So therefore we can see that this is actually true.